So I'm here again in Cannes with Pablo Jorba, project manager for the Plato mission at OHB Systems in Munich, Germany. And he's here at Thales Alenia Space. We've been talking about the Plato mission. And Pablo, tell us a little bit about the unique configuration of the difficulty in integrating the design and the integration of the individual cameras. There are 24 cameras plus the two the two cameras which are used for guiding the spacecraft. So what were the design challenges and the integration challenges for dealing with so many different cameras which are not interferometrically linked? You're not combining the light in an interferometric sense, but you are combining the light into individual pixels. If you could explain how that works.
So basically what we are integrating is an optical bench with 26 cameras, as you have said, 24 that will generate science data.
And it's not a hexagonal,
No.
Nor is it
No.
How would you describe it?
So what we have is like a stepwise stairs approach, our optical bench. We have 6 cameras per row, so making a total of 24. So we have 4 groups. And then we have 2 cameras on top that will be used for fine pointing guidance. Yeah? The challenges are manifold. Yeah? On one side is the logistic aspect, but on this one we are cooperating with ESA, who is providing to us the cameras. For us, it's a custom foreign item. And what we are doing is that we are mounting to the optical bench, we are characterizing them optically, and we are aligning. So we are talking about an alignment in the 10th of arc seconds, so it's quite important. And we are integrating the 26 of them, doing small functional test on each of them. To reach to this point, it has been a really complex and challenging path. So we started with a structural model in which we mounted dummies, and we performed several tests. I think they are quite challenging and unique to characterize the thermoelastic distortion.
So the thermoelastic distortion.
Yes.
Explain what that is.
So thermoelastic distortion basically is that when you have some changes and gradients in temperature in a structure, what you will have is that different surfaces will come a little bit. So the effect is that you can be mounting in certain thermal conditions like ambient a camera, but when it is submitted to vacuum or it's submitted to thermal gradients because of the space, what you will see is that the camera will tilt and will change a little bit. So because of the importance of overlapping, so what you have said to detect the change in luminosity in pixel by pixel and the importance of having them overlapping, small thermoelastic distortions could have impact on the measurements that we are doing on the stars. So this is really important that these, among other aspects, are really taken into consideration. Another one that we have not talked about is the effect of microvibration. So we are pointing...
the effect of, can you repeat that?
Yes, the effect of microvibration.
Microvibration.
To make a simile, if you have a camera and then you are pointing to a quite far location, if you have a shaky hand, what you will see is that the pixel will move up and down because you are pointing to something that it is really, really far. So this is also a key driver aspect for the Plato mission, in which you have to have a really good decouple, that things that are vibrating or things that are moving, like the thrusters or like the reaction wheels, to keep the attitude of the system, are not affecting to the pointing that you are having. So this is also another challenging aspect that had to be taken into consideration in the Plato design to avoid that you have this type of shaking effects.
And so what about, if you could explain again what Plato is doing is it's taking individual photons or streams of photons from all the stars that it's looking at, that it's observing. And how does that translate into putting the photon in the photon buckets or the photon pixels, or how does it actually work?
In general guidelines, what we are having is that each camera has a detector, 4 detectors that are overlapping each other. Yeah. And then you have a star that it is projected into both detectors in different pixels. So the processing, in simplified way, is that you take the analysis, you analyze the change in luminosity on each of these pixels. You know which is the relative pixel in the second camera that is pointing to the same star. And then you start analyzing how much the star brightness is affected, as far as you are getting more and more detectors, more and more pixels, what you are increasing is the signal to noise ratio, just to make sure that small changes in luminosity because of a transit of a planet, transit of a comet, or transit of whatever,
or the variation in the star itself.
or variation of the star itself.
Yeah.
Star itself, exactly. So what you are doing is that you are doing some sort of, let's call it a stacking, in which all this information is merged, just to provide to the scientific community, which is the change in luminosity, and to be able to detect which is the cosmological elements, or mainly planets, Earth-like planets, that are passing in front of the stars.
And so if you could explain a pixel itself, it's a digital, so in other words, when we look at a star on a beautiful sunny or a beautiful evening, like the ones we're having right now here in the south of France, we see these beautiful points of light, and we visually detect them. Our eyes, our retina visually detects these photons. So what you're talking about is a electronic device, a camera, that is taking these photons, visually detecting them, but turning them into a digital signal. Is that correct?
Usually what you have is that you have a photon that is hit into the detector.
It hits the detector.
It hits a detector, so it's the surface of the detector focal plane. So what you cannot do with your eyes is that your eyes are really bad integrating. So you see a small point, but it is not able to record these photons, your eyes. But what you have with the detector is that you have a photon, and then it's creating a small charge on this detector, and then what you are doing is accumulating it. So it's what it is called integration time. So you get more photons, you get more electrical signals, and at a certain point you say, okay, I dump this to the data processing system, who is in charge of reading, processing, and then to send to ground this data for later scientific processing. It's similar than when you have a normal camera in a mobile phone, and work in a different way. You have different technologies, but basically it's a photon that is hitting a detector, and then you get some charge inside this detector that is later acquired by an electronic system.
So two last questions. The first is that even a camera like this, even I'm shooting this on a video, a handheld video camera, which has astonishingly, great quality. But how would an individual camera in one of the 24 cameras that you're using for science on Plato, how would the resolution on your cameras on Plato compare to the resolution that I would get in the photo mode on this camera?
So at the end, if I'm not wrong, if I remember well the number, so the total 26 cameras are creating like a big camera, that is acquiring the data, and I think it's in the order of 2.2 gigapixels. So if you put in context with the normal cameras that we are talking about megapixels, so we are talking about several orders of magnitude higher than what you have in normal mobile phone. With also the fact that you are looking into a space, so if you compare the situation here with Earth, you have the atmosphere, so that it is making really complicated in some cases to get the proper picture of the star. But in space, in Lagrange, in the Lagrange point number 2, that you have no interference of the sun that we will have in the back. You are looking completely dark space with super precise and detailed.
So aside from interstellar scintillation caused by dust, there's really nothing to interfere with your field of view. And so I guess the other point is that even people with great eyes could probably look at images created, images from the Plato mission after it launches, and would not be able to appreciate the difference between the visual images that you're creating and the images on a camera. But they're there.
They're there.
But even though our human eye can't detect it.
No.
So then the final question is, this project actually started in 2014, you were funded in 2017, and you've been able to bring it in on budget and on schedule thus far. We hope that, keep our fingers crossed.
Yes.
But you even went through COVID, and COVID was a bugaboo for a lot of aerospace companies. How did you cope with getting the parts for the cameras, the necessary ingredients to make this happen during the COVID epoch?
So during the COVID period, we were also in a situation in which, so you had manufacturing, but it was mainly a phase of design. And what I would say is that the cooperation within Plato, it has been really, really good. So there is big trust between the different companies. So it was always, so not only because of the motivation of the companies, but also we were working together to find solutions to the problems. It's not only the OHB problem, or it's not the problem of Thales or Beyond Gravity or any of our superconductors. I believe that we have made all together Plato as a part of ourselves, and then we have been working together to try to minimize these effects. Of course, COVID had an impact, but I think the results of a fully consolidated and stable schedule from 2018 till today it really indicates that we were able to cope really good with the COVID time, and this is the result today.
So thanks so much, Pablo, for your time today. Good luck with the mission, and we look forward to following your progress.
Thanks a lot.